Awesome. Okay, good morning. So I would like to talk about our paper about requirements, abstract state machine, executable abstract state machine, and how we can test them using our proposed method. So I would like to introduce a case study for the rest of this presentation here. So we're going to consider an e-health system. Let's see what the major components are in the system. First of all, we got patients, we got medications. The patients are prescribed to medications. However, medications might be dangerous with each other. For example, warfarin might be dangerous with aspirin. Okay, just one example. So what would be the goal over here to preserve the property for the system? The goal would be there should be no dangerous interactions between any of the prescription for a particular patient. We want to make sure this is a global property that's imposed. So given that, I can propose our research problem here. Because typically, if you want to specify your system or implement your system, you got some kind of informal requirements, but how can you make it to eventually the working code? So given informal requirements, like what I just said about the e-health system in the problem domain, how can we facilitate the process of developing working code in the solution domain? So over here, I emphasize is the process. So we do not want to jump directly from problem into solution. We want to have some intermediate specification that is both precise and executable, so we can run some tests on our specification for the requirements. So that would be our proposed method overall. We want to develop any critical system, safety critical system, or mission critical system in the same way. So now let me go over the contributions for our paper. Okay? There are two major contributions for this paper here. Let me just go over one by one. The first one is called ETF, standing for IFO Testing Framework. And there are two aspects of this ETF. Let me just go over them with you. Okay? So now you can see my notes over here. Let me just go over that. So this diagram over here, let me try to highlight the main components for our contributions. The first component is called ETF. Over here, IFO Testing Framework. The first aspect is ETF is a code generator for business logic stop. How does it work? So now, first of all, for any problem you're trying to solve, you have some informal requirements document to begin with. I will show you a good method for documenting your requirements in just a moment. But now, given the requirements document, what we want to get, first of all, is some abstract user interface grammar. So here I emphasize the term abstract, because at this point, we don't want to prematurely commit to any concrete GUI components like a radio button, drop-down menu, or text box. We don't want to. At the moment, we want to focus on modeling precisely what the customers need. So abstract grammar. And what the ETF can do for you. Given this grammar over here, even the customer who are non-experts can actually specify this grammar together with you as engineer. So now we've given a grammar and pass that to ETF. What you will get is some architecturally structured executable code. What do I mean architecturally structured? So I will just briefly mention that our generated code by ETF conforms to a number of well-known design patterns: observer, singleton, and also command. I'll show you briefly. And then you can see in the generated code, we have clear separation between user interface, package, and also the business model package. So this is the stop that I talk about. It's a placeholder for you to gradually develop your business logic. That's the first aspect for ETF. The second aspect is for the customer, given the abstract user interface, they can also specify how exactly they would like different use cases to work. They can say, given this particular states, given this state updates, I want this particular resulting states, right? They can specify as many as they like. So that's the acceptance case. And now, given that this generated code is executable, so given that you have your acceptance test given by the customer, you can, of course, test it at the runtime to see if the acceptance test will be passed, okay? So that's about the first contribution about ETF very briefly. So we got these two aspects. And here, acceptance tests are in contrast to unit testing or integration testing, where the developer should know the internal workings of the code. But in this case, for the acceptance test, no, it can be done by the customer side. The second contribution is so-called the math models programming library implemented in the IFO programming language. So now, about the math model, let me show you again. Remember, as said before, there is over here, the package over here as a placeholder for the business logic. But now the question is, how can I develop my business logic gradually? it may not be so effective if you jump directly to coding to say, oh, maybe I should choose a binary search tree. Maybe I should choose a hash table. Maybe I should develop my own data structure. It might be a little bit too early. So what we advise is go back to discrete math and think about in terms of relations, functions, sets, and back, and see how you can come up with abstract states and their corresponding updates. So that's why we got this math models library for you, so you can use all sorts of mathematical concepts to document your design. And over here, the math models can help you create abstract state machines. Abstract in the sense that it's not exactly the efficient data structure you will finally commit to. You can definitely refine that eventually into the efficient data structure. It is executable because in the math models, we also support methods that will help you manipulate the objects. I will show you example for the math models. So these are very quick go through of the math models library. So these are the two contributions. And as a remark, we claim that our the method we are presenting here is scalable to large system because everything is done in the IFO framework, which means we can use the IFO programming IDE for free. And then any large system, we can simply run acceptance test at runtime, as opposed to theorem proving or model checking, where you do have the inherent limitations on them. Okay, that's about the contributions. Let me just now go through each ingredients one by one. The first one I would like to talk about is something called requirements documents. Let me just show you a way by Jackson about how you can document your requirements. There are two categories of requirements. One is called E-description for environmental constraints. And the other one in the next slide is called R-description for documenting the functional requirements, what the computer must produce. Let's say in the case of the e-health system, let's just go over what the E-description might be and what the R-descriptions might be. So for each description there, we assign a unique ID over here for the purpose of traceability later. So later on, when we generate using ETF, the executable code over there, we can also make a tag to say environment 1 constraints reflected here, and maybe requirements number 6 is reflected here. I will show you example. So now, constraint number 1, physicians prescribe medications to patients. Number 2, there might be dangerous interactions. Number 3, it's symmetric. If warfarin is dangerous with aspirin, then vice versa must be true as well. Number 4, a medication does not interact with itself. Aspirin is not dangerous with aspirin itself. Okay, so these are the 4 properties we have. Questions?
You also have combinations of 3 which are dangerous?
Yes, so in this case study here, we consider just 2, like a pairwise. Yeah, good point. But I believe you can also specify the ternary relation or n-ary relation using pairwise. Yeah, good question. Yes. Okay, so now that's about the environment constraint. Let's talk about functional constraints over here. Number 5, you can see the numbers continue from number 4 from the previous slides. The system shall maintain records of dangerous medication interactions so that every time, if you want to add a new prescription, you can make reference to it. Number 6, the system should maintain records of patient prescription and no prescription may have a dangerous interaction. That's exactly the goal I just talked about in the previous slides.
You can also have 2 different prescriptions, one with one dangerous component only, and the other with the other.
Yes, that's a good point. I think that's kind of handled in our system. Yeah, I'm not too sure in the fragment that I show on the slides is actually there, but when you actually consider the relation globally, you will be covered. You will be covered, yeah. But that's a good point, yeah. Okay, and number 7, and later on you will see how requirement number 6 is traced back to, will be traced back here from the code. And requirement number 7, physicians should only be allowed to add a medication if it does not cause any new dangerous interaction, right? It does not cause any conflict in the prescription. Number 8, it should be possible to add a new medication provided that it does not cause any new dangerous interaction in the existing prescription, right? It's kind of a similar idea here. Just for number 7 is to add a new prescription. For number 8 is to add a new medication. You got a similar goal. And then finally, physician may be allowed to remove medication for as many as they like because it wouldn't cause any new dangerous interactions. So, okay, so these are the R descriptions. So far we covered just about some example of how you can document the requirements using E and R descriptions. So the next one is abstract user interface. Remember in the previous slide over here, I talked about given the abstract grammar over here, we can pass that into ETF to generate code stop. Let's see how the abstract user interface can look like. Okay, we got a system, eHealth. We can define as many types for semantic type as we like. In this case, just simple ones. For the more sophisticated one, you can refer to our paper. So we say that medication is synonymous with a string, and patient is synonymous with a string. Just give a name. You can make it more complicated for your need. And then we got different events or state updates. Okay, we got add patients, we got add medication, add interaction, add prescription, remove, and remove prescription as well. Okay, so you got different events over here. Okay, and so now, as I said before, at the moment, you can see this is very abstract. We are not really showing any radio buttons or any concrete GUI components. Okay, the next one to show will be, once you know about roughly how your system works as an interface, you can define abstract state variables using set theory and using the set theory. For example, patients are a set of patients. Medication is a set of medication. Interaction is a relation between medication. And then prescription, relation between patient and medication. And so now let's just see some example of this abstract state definition. You can see patients can be P1, P2, P3. Medication, N1 up to N4. So we say that in medication, we can say N1 dangerously interacted with M2 and vice versa. And then we say prescription, P1 is prescribed to N1 and M3 and etc. Okay? So given these information here, let's now write some acceptance test, which I will show you. Okay? So now let's go to the iPad over here. So now given that we already got the abstract user interface, we got abstract state variables, let's now write the acceptance test. Okay, I will just do it quickly. So now I would like you to say, okay, let's say for now we are now in state 16 for some reason. And then we got P1, P2, P3, 3 patients. And also we got 4 medications over here. I want to draw your attention to M2 interacted with M4 dangerously and vice versa. Okay, these are the 2. And then notice that patient number 3 is currently prescribed to M2. What does that mean? That means if you try to add N4 as P3's new prescription, it should not be allowed because there will be some dangerous interaction. So that's why we see some error message over here. Okay, you can notice that the user interface has implemented some error handling mechanism rather than crashing your app. Okay, so you can just continue with that, and then we say once we remove the dangerous interaction, and now you can prescribe both M2 and M4 to the same patients. Okay, that's just one use case which can be written by the customer. Okay, let's go back here. Okay, now I want to just show you very quickly about how the ETF can be used very quickly. Okay, so now I want to show you over here, let's say I'm now in the directory of eHealth, and the only file I have is the abstract UI, which I just show you to, right, the ASCII form. And ETF is actually a command line tool which I can just use by invoking ETF-new for generating a new project, and then the abstract UI file, and then in the current directory. If I do that, it's going to generate all sorts of files, including implemented parser for you to parse the acceptance test. I wouldn't go into details for this. I just want to show you, once you have generated a project, you can simply just go to the iPhone Studio, the programming IDE. You can see it's nicely structured. You can see that I talk about the, so they are basically this is the abstract UI package, and that's the model package, right? By default, model will just be default model, which is just a placeholder. You should gradually refine this into your eHealth system classes. Okay, over here, I just want to continue with the slides. Okay, so that's about the, so you can see over here, that's kind of the structure. We got user commands, we also got model. And here we actually got the command design pattern over here. We also got singleton pattern, making sure all the commands share the same instance of the eHealth system. We also got observer pattern, which means every time when the user sends the request for system change, we should publish the result back to the UI. Okay, it's like a model view controller separation of concern. Okay, that's about it. Okay, so now, finally, the question is, how can we develop the business model in the model package? So the answer is, use the math models library that will support. So we got, for example, relation class, which is a set of pairs or tuple. And we support all the standard domain, range, and image. And also here we got immutable queries for writing precise contracts, precondition, postcondition, and class invariants. You can see given some arguments, you can return another relation, so that's immutable. Also just 2 examples, extended and also overridden by. And for every query, you also have mutable command, which does not return another relation. That's just more like a Java standard method for adding something into a list or appending something to a string. Okay? So we got, so the green ones are for you, okay, let me just see. The green ones are immutable query for you to write precise contracts. And the red ones over here are for you to implement your abstract state machines, and you can test them. And later on, you can refine your relation, for example, into a hash table or a binary search tree. Okay, that's something later. But once you get a mathematical model set up, it should be rather straightforward to refine them. Okay, so now I want to show you again very quickly about what's the advantage for math models. Let's consider again requirement number 6. How can we make sure there is no dangerous interaction? Okay, very quickly, that's how you would specify, how you would formulate it using set theoretic logic. Okay, basically you're saying that if medication 1, medication 2 are considered as dangerous, then they should not be the same prescription for the same patients. Okay, they should not be actually prescribed to the same patients. That's about the math. But this math is here is not executable. How can we test it? The answer is you can straightforwardly translate it into math models in IFO. How do we make it traceable and also executable? So in IFO, you can declare a tag for all the contracts. So let's say here for traceability purpose, we just say requirement 6. And then we can use, I wouldn't go into detail, but the across syntax is like a for all quantifier, universal quantification in IFO. And then you can see the color over here. So if the prescription has M1 and M2, then it shouldn't be the case that the 2 interactions are dangerous. You can see the close correspondence between the math and also IFO, the math models. That's really the advantage for using math models to develop your business logic. Okay, finally, I want to give 2 examples of how you can use the math models to define 2 things. First of all, we can define the safety constraints for your class. Okay, let me just go over some details with you very quickly. So over here, we have a class called health system here. And then, so these are the abstract state variables that we already covered. So now we can now define safety constraint. What does it really mean for your system to have integrity and not to be compromised? So the first one is we can define a symmetry constraint environment 3 that can trace back to our requirements. Okay, for the corresponding IFO code, you can just refer to explanation in the paper. And also we have irreflexivity for environments constraint 4 that can be traced back to the requirements here. And also we have no dangerous interaction rec 6, which you already went through in detail, and that can be traced back here. Okay, so you can see the traceability can be nicely done in our case from code back to requirements. Okay, finally, I would like to go over how you can use math model to specify state updates using precondition and postconditions. Okay, so now over here, let's now have a look at this. I want you to consider requirements number 7, which is about physicians should be allowed to add a medication if it does not result in any new conflict. Let's see that. So here, first of all, we can see that we have a class called add prescription. It inherits health system. What does inheritance here mean? That means it's going to inherit all the safety constraints we defined in the previous slides. Okay? And then we define a feature or method called add description. And we have these 2 arguments, patient and medication. Let's just go over very quickly. For the precondition, we want to make sure the patient exists in the system. And also, we want to make sure the patient is not already prescribed to this medication. And also, most importantly, we want to make sure for all the medication that has been already prescribed to P, patient P, they should not have any dangerous interaction with the new medication you're trying to add in. Okay, so these are the preconditions. And let's look at the postcondition here. The postcondition is simply that the new prescription should be exactly the old prescription appended with a new prescription, right? The new medication we're trying to add. Okay, now one more thing to point out. In this section over here, which is the body implementation. So what we just talked about in orange are the contracts, but the green one is the body implementation. That's why I said our state machine is executable. You can see the extend here is a mutable command. So that means it's just like a method that you can execute. But later on, you can refine maybe from, in the previous slide, maybe you can refine from relation into hash table. And then over here for extend, you can refine that maybe to put, like a key and value pair, in Java. So those are the later stages. It's not out of the scope for this particular paper. Okay, finally, I'll make a conclusion. So for this paper here, basically, I just want to show you the two contributions we have for the paper. We got ETF, which is a code generator, and also we got math models, which is a programming library for you to specify contracts of your business model, of your business logic. And that's a diagram I have went through in detail. Finally, because we are using design by contract and also using the IFO programming IDE, so we claim that it's somehow scalable to large system because we're only doing testing as opposed to theorem proving or model checking. Okay, I'll be happy to take your questions. Yes.
Thank you, Chen Wei. I think Ali is discussing the paper, so you get first pick, and then Oscar has the question.
Yes.
First of all, thank you for the presentation. My first question was that you mentioned that by the requirements, we just generate an abstract interface.
Mm-hmm.
And then we generate the test cases.
Mm-hmm.
Now I have two questions.
Yes.
First of all, how do we deal with the models, the large models that interact with other large models, modular models that share variables and the requirements are separate? So we cannot test what the other model, how the other model affect this model.
Okay, so basically the question is, how do you deal with a system where maybe modules interacting with other modules? I think that's maybe more at the level of the business model level. So basically, in the abstract user interface grammar level, we simply say what can be the system events. Let's say you have an ATM machine. What are the buttons there that the customer can interact with it? But how you actually develop like a modularized design for different classes or different packages, like what you said, it should be at the business model level. That's just like a normal programming practice.
And my second question was that, so after we have this abstract interface, then the tests are defined by developers, right?
Oh, good. So the question is, who developed the acceptance test? It can be the customers, because as you can see, the acceptance test I showed before, let me just go there very quickly. You can see that it's in ASCII formats and it's quite easy to understand, the one I just showed you. Okay, let me just go there very quickly. So this is the acceptance test. It can be done either by the customer together collaborating with you as a developer, or it can just be you as a developer to develop that. So it's actually follow the syntax that's not specific to any programming language. So any non-expert can do. Yeah.
So is there any way that the system can generate test cases?
We are currently not considering about generating like the abstract user interface or test cases. It can be the future work. Yes. Yes.
Well, first of all, it's the running system is implemented in what environment?
Environments, it's a programming environment called IFO. So IFO was invented by Bertrand Meyer in ETH in Zurich. So the advantage.
You're talking about
IFO,
No,
yeah.
I'm talking
The acceptance test.
about your prescription system.
Mm-hmm.
It's in Java or so, some object-oriented environment.
Oh, you're talking about the e-health system? Basically, I was just presenting that as just a general simplified system just for discussion. So I'm not committing to any particular system over here. I'm just saying.
I thought it generates code, so there can be a running system in the end.
This indeed a running system, but since we are just trying to study a simplified problem over here, saying we got patients, medication, dangerous interaction, and eventually, of course, we can get more executable code. But let's say if you want to get more complicated, more sophisticated developments, maybe for your company, you can definitely revise the abstract user interface and generate ETF, using ETF to generate the code accordingly. Yes. Mm-hmm. Yeah.
Thank you for the presentation. I think that it was very, very clear. I think that I have well understand what you are doing.
Thank you.
It's really promising. I have a couple of questions. The first one is related to the functional view of your work. I mean, functional perspective. I mean by that I guess that non-functional requirements are out of scope right now. You are just focusing on functional requirements. So Is it true or not?
Yes, we do focus on functional requirements. Like we got E description for environmental constraints, and also R description for what function you want to implement. So these are the only two.
Because testing the functional requirement will be another issue. It's a kind of meta testing because the work is very dependent on choosing the right functional requirements. So if the requirements are not well chosen, everything
true.
are under problem.
Yeah, maybe.
It's like this also. This is what happens.
Yes. So let me just, it's a good question. Let me just clarify the scope for our contribution just for now, very quickly. So now let me just go back to this diagram over here. So basically our main contribution for this paper here is basically this and that. And what about this part you just talked about? That one is kind of, we assume is kind of given from the requirement elicitation. So the example we gave to you, just one example. That's one way you can document it.
Is the work fully dependent on Excel, or do you think that I think that what you are doing could be applicable to other programming environments?
Yes.
But you are just focusing on Excel. So what about this working?
Mm-hmm. So good question. The question basically is why IFO? Why not Java? Why not C#? So the main reason we chose IFO was because you can see that from this diagram over here, math model is a very important component for you for developing the business logic. And we think the most effective way to develop your business logic is by using decide-by contracts. Decide-by contract is only natively supported with all kind of runtime assertion checking in IFO. So we think IFO for now would be the good choice. But maybe you're right, maybe Java and C# might be more popular in the industry, but we think as a good practice, IFO would be the way to go.
I think that the concepts that are behind what you are doing can be generalized.
Yeah, we just need to find a way to see how we can do decide-by contract more or less approximately the same way in other languages. Yeah.
I have a follow-up question on that. Some of the slides that you showed to me that looked a lot like OCL. What's the difference between your approach and OCL?
Sure. The difference between ours and OCL, I think I tell you what, the example I show you for the purpose of this talk, they are rather simple. So I think let me put it this way. So OCL is more like a specification language. So, and it has some limited syntax. It does not support like everything it can do as a programming language in IFO. So the way we implement the math models library in IFO, we simply use a native IFO syntax, which means you can support very expressive features or commands or queries for mathematical models, which we cannot find the corresponding counterparts in OCL.
Okay,
yeah.
great. Thank you very much.
Thank you.